Hi guys, today we're going to talk about energy conservation. Right now, I have the potential to move. I have potential energy. And in this video, you're going to learn about what that is and also the energy of this.
So let's start with the basics. There are two types of energies, kinetic and potential. These types of energies are fundamental for the conservation of energy formula that we will be talking about later. But for now, these two types of energies are measured in standard SI units. So everything will be measured in the metric system. For example, they'll be measured in kilograms, meters, joules, and seconds.
Now let's talk about translational kinetic energy. Translational kinetic energy describes the velocity of an object as it moves through space. Translational kinetic energy uses the equation of 1/2 mv squared, or half of the mass of the object times the velocity of the object through space squared. Now, velocity also has a rotational counterpart, which describes, you guessed it, the rotational kinetic energy. It is described as 1/2 I omega squared. I, in this instance, describes something called the moment of inertia, which is a rotational analog of mass. I describes mr squared, which is the mass distribution of an object. Omega is the rotational counterpart of velocity. So 1/2 I omega squared is the same thing for a rotating object as 1/2 mv squared for an object that is moving through space. An object that is rolling can have both rotational kinetic energy and translational kinetic energy.
An important thing to remember about all of our energies is that it's something called scalar. Scalar refers to the quality of a variable that means that there is no direction and only magnitude. What this means is that we're never going to have negative energy. Energy can only be transferred, lost, or dissipated, but it will always be positive.
The reason why is because in our equation 1/2 mv squared, or 1/2 I omega squared,
the omega and the velocity are squared. So even if the velocity is negative or the omega is negative, because the values are squared, they are being multiplied by themselves, and the negatives will drop out. Therefore, energy will always be positive. Now we're going to talk about potential energy. Potential energy describes the ability of an object to do work because of its position, shape, or state. The condition that an object is in when it has potential energy describes the ability it can transfer that energy into other forms of energy, such as kinetic energy, which allow it to progress linearly or rotationally. Gravitational potential energy described as mgh, which describes the mass of the object, the gravitational acceleration, which is 9.8 meters per second, and the vertical distance from the Earth, which is h.
Now let's get to the bread and butter of the video, energy conservation, otherwise known as the first law of thermodynamics. The first law of thermodynamics follows a simple formula, EI equals EF, also known as the initial mechanical energy is equal to the final mechanical energy. This breaks into a much larger formula though. It's not that much larger though. So it breaks into the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. This is where the formulas we learned previously come into play.
Thank you, Charlie. Now we're going to use this equation in a real-life situation. So over here I have a block at the top of the slide. Right now it has maximum gravitational potential energy. Because mgh, the vertical distance h, which represents the distance from the block from the surface of the Earth, is at its maximum. So in our equation we have EI equals EF, and we have kinetic energy initial plus potential energy initial equals potential energy final plus kinetic energy final. And we can see that we have mgh on the left side of the equation, which is at its maximum. And because the block is at rest and has no velocity, our kinetic energy, 1/2 mv squared, will drop out. So right here, we're looking at the block when it is in the middle of the run. So if we look at our EI equals EF equation, we actually do have gravitational potential energy because it does have a vertical distance from the surface of the Earth. So we do have mgh. But what we also have is kinetic energy because it is in translational motion down the slide. So we have both. Now this is actually going to be our right side of the equation, because if you remember in the beginning, for our left side of the equation, the only thing that we had was mgh, because the 1/2 mv squared dropped out because there was no velocity. So now we're looking at the block when it's at the end of the run. And we already know that for the initial energy, we said that it was mgh because the kinetic energy dropped out. And now for the final energy, we see that there is no gravitational potential energy because there is no vertical displacement between the block and what we are saying is the surface of the Earth. So mgh, we'll still write it, plus 1/2 mv squared. But again, this mgh is actually going to drop out and become 0. So now our whole entire equation is mgh equals 1/2 mv squared. That is for the entire duration. We can also say that all of the potential gravitational energy was transformed into kinetic translational energy, which resulted in positive work translational.
Now on to spring potential energy. Spring potential energy is the energy stored in an object when it is stretched or compressed. It can also be known as elastic potential energy. The formula for this energy is 1/2 kx squared. K is an arbitrary constant based on the strength of a spring. It describes how hard it is to stretch or compress the spring. And x is the distance stretched from equilibrium of the spring. So, for example, if I have a string right here and I stretch it, the spring potential energy will increase because I've stretched the spring farther. Therefore, the x is increasing.
So now we're going to step into the world of rotation. As mentioned before, kinetic energy has a rotational counterpart. So we're going to go look at this through the lens of a cylinder rolling down the slide. At the start, it has gravitational potential energy like any other system. But when I roll it down the slide, it has both translational kinetic energy and rotational kinetic energy. How this fits into our energy conservation equation, we have to add our rotational kinetic energy formula onto the right or final side of the equation.
One trick the AP will love to play on students is they'll give you the mass and the velocity only and ask you to calculate the initial energy of the system. How do you do that, you may ask? Well, as we learned, the final mechanical energy is the exact same as the initial mechanical energy. So you can just calculate 1/2 mv squared, or the final kinetic energy, and use that to find the total energy that was at the start of your system. This is only applicable if it is an ideal situation where there is no non-conservative forces present, like friction.
Another thing that we're going to talk about briefly is something called work. Work is the transfer of energy from one form to another. So we saw this briefly with mgh turning into 1/2 mv squared in our ideal situations. And what this was doing was a positive work translational from gravitational potential energy into kinetic translational energy. Or in this instance, with the cylinder, kinetic rotational energy positive. But we're also going to have something called work non-conservative. This is actually going to be taking energy away from the system. Because if you see up here, all of these are conservative forces. The force that's pushing the cylinder down would be the force of gravity. That is a conservative force because the mgh is turning into 1/2 mv squared. But work non-conservative, which describes the forces of friction, are going to be taking energy out of the system. So a force of friction actually just opposes the intended motion. And so how we incorporate it into our EI equals EF situation is we have it like normal, like let's say it starts at rest, mgh, so there's no 1/2 mv squared, it drops out. And then on our right side of the equation, let's just say we have 1/2 mv squared. This is in an ideal situation when there is no friction, but we do have friction. So we're going to actually add work non-conservative to our left side of the equation. And the reason why is because if you are adding friction initially, the result of this will be negative work non-conservative. So if we have negative work, that means that energy is being taken out. The reason why the work is negative is because it is accounting for external forces. By itself, the force of friction is technically a quote-unquote positive force, but because it is a vector and denotes direction, the resulting work from the applied force of friction will be negative because friction is opposing the intended motion. Therefore, it is resulting in a negative work translational.
This means the final energy will be less than the initial energy.
Okay, so the situation here, pause to read the problem. The situation here is that we have a horizontal spring that is oscillating. I'm going to really quickly draw out what the problem looks like. So we have the block here, and we're going to say that right here is our equilibrium. This is when it's an initial. So we have our 40 kilogram block. And right now that the distance from equilibrium, our first x, is 7 meters. And I'm just going to go ahead and say that our right is our positive direction. But then, and also the block is at rest. Then the block is released, and what actually happens is now the block is to the left of our equilibrium. And because it's to the left, it is 3.5 meters from equilibrium, but that's actually going to be negative because it's in the negative direction. It's the opposite of left. So we're going to start with our EI equals EF equation right here. We're going to go EI equals EF. And because it's frictionless, we're going to say that there's no work non-conservative, so all mechanical energy is conserved. So when it's here and when it's held at rest, this initial displacement, 7 meters, is actually going to be our maximum displacement. So I'm going to go ahead and use blue for potential energy. And we're going to first extrapolate this problem. So we have potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. But here's the situation. We said that velocity was initially 0, so that's going to drop out. And we also know that our potential energy formula is 1/2 Ka squared. And the reason why I'm using A is because this is our amplitude. Our amplitude is our maximum displacement from equilibrium. And our x1 is our maximum displacement because the velocity is 0 and is held at rest. So I'm going to say 1/2 Ka squared. Now this is going to be all that's on our left side of the equation. Now let's look at our right side of the equation. So we do see that there's still potential energy because there is compression from equilibrium, which is negative 3.5 meters. Remember, the negative doesn't mean anything about the magnitude of the value. It just refers to the direction. So I'm going to go ahead and write 1/2 Ka squared. And we also have velocity because it says that the block is moving and it wants the velocity of the mass. So we're going to say 1/2 mv squared. And we want our velocity. So what I like to do is I underline it. So now we're going to plug in our values. So we know our K value is 10. So we're going to go ahead and plug that in. And we know our amplitude, our initial displacement is 7. So we'll plug that in squared. And then we'll do the same thing over here. 1/2 10. I meant to write X here. I'm so sorry. And we know that this is negative 3.5. So we're just going to put a negative 3.5 here. And that's going to be squared. And then we have half of our mass, and we're going to take the mass of the block because we're assuming that the spring is massless. We're going to say 1/2 of 40 times the velocity final squared. So now what we're going to want to do is we're going to isolate velocity. Because mechanical energy is conserved, we know that all of these values here will equal this velocity value here. So we're just going to go ahead and evaluate that. We know we have 245. That's on our left side of the equation. Now we're going to take a look at our right side of the equation. We have negative 3.5 squared. And remember, because energies are scalar, even though that the displacement is negative, it's an energy, and so it's scalar. And so when we actually square negative 3.5, which becomes 12 2.5, the negatives drop out. So we have 12 2.5 times 5. Which is 61.25. Now we add this to 1/2 of 40 velocity final squared. And so we have 245 minus 61.25, which is 183.75 equals 20, which is half of 40 velocity final squared. Now we're going to divide 183.75, our left side of the equation, by 20. And we get 9.18 equals VF squared. So the square root of 9.18 is velocity final. And we evaluate that 0.03 meters per second is our final velocity. So the situation that we're looking at here is it's asking us to find the work from this force versus distance graph. So we know that work is the integral of F with respect to dx, which is respect to position. And we know that the integral is the area beneath the curve. So what we're going to do is we're going to take the area between the function and the axis, and that is going to tell us what our work is. So what I like to do when I'm taking the area beneath a function is I like to separate it into shapes. So we have the rectangle here, and then we have a triangle here. So we're just going to start with the area of a triangle, which is 1/2 base times height. And we know that the base is 8 meters, and we know that the height is 30 meters. So we have, 30 newtons. So we have half of 8, and we have 30. And this is going to evaluate 120. And then we have the area of the rectangle here. So we're actually just going to evaluate from 8 to 12, which is going to give us 4. And the area of a rectangle is base times height. So our base is 4 meters, and our height is 30 meters. It's also going to be 120. And so now we're just going to add these two values together to get our area under the curve, or our work. So we're going to get 240 is our work. Instance that we see that is really popular on the AP exam is it will ask us, given this graph here, to evaluate it, and it'll ask us the change in energy between positions 4 and position 8. So what we're going to do is we're going to start at position 4, and we are going to evaluate the area under the curve, which we just established would be our work, so our change in energy between x equals 0 and x equals 4. So we're going to take the area of this triangle right here. So we can see that the base is 4 and that the height is 15. Multiply those by each other, you get 60. And then divided by 2, which is the area of a triangle, you should get 30. So we're going to say that 30 joules is our work at x equals 4. And once again, evaluating this piece here, even though it's between x equals 4 and x equals 8. You're taking the total amount of work, which is the total amount of change in energy. And so at this point, because it's positive at whatever your final position is, it will denote what the amount of energy in the system is via work. So we just established that 30 joules is at x equals 4. And so at x equals 8, we have the base of 8 and we have the height of 30. Multiplied by each other is 240. Divided by 2 is 120. So we have 120 joules of work of energy at x equals 8. And now because it wants you to find the change in energy between these two values, or between these two positions, we're going to subtract them from another. So we're going to start by writing work equals, and then 120 minus 30 is 80 joules. And then as a subscript, we're going to write between position 4 and position equals 8. That tells us is between positions 4 and position 8, there was a change of 80 joules. Now, whether that is positive or negative work depends on the direction of the force. We can see that it is in the positive y direction, so we can denote that this is positive work done, because remember, work is the integral of f dx. And so we can see that this is positive work.